To finalize our set of videos for this week on raster data and remote sensing, we're going to talk about remote sensing. Look at that. Remote sensing on our screen, doing remote sensing stuff. Remote sensing is its entire own field of practice, its entire own way of doing things, and its own class. I say a lot, I think, in Intro GIS here that there's another class on that topic, another class on cartography, another class on spatial statistics, another class on remote sensing, but we are going to interface with it. So we've got to think about it a little bit. So here we are. This is remote sensing in a diagram, in a quick diagram. The whole idea of remote sensing is that we have satellites that are gathering information about the planet, and that planetary information is generally gathered in this way. The sun radiates energy to the planet. It's why we're here. And then that energy is then reflected off of things on the planet to a satellite, and the satellite measures that reflected solar radiation. The majority, vast majority of our remotely sensed data is reflected radiative data, meaning that it is solar radiation that has come from the sun, bounced off the planet, and then hit the satellite. There are some infrared data sets that is emitted data. So infrared is heat information when the Earth emits it, but most is reflected solar radiation. Now, as that is bouncing off the planet back to the satellite, different things bounce energy differently. So an urban area will bounce energy different than a road, than soil, than water, so on and so on and so on. They also bounce differently based on different wavelengths, which we'll look at in a minute. So the sun is broadcasting all of this different type of electromagnetic energy. We see what is within the visible spectrum, but there's a lot more to it, and remotely sensed data uses a lot of non-visible spectrum information. So it's very fun. So remote sensing satellites are gathering this data. Mentioned in a couple recordings before that sometimes this data, or sometimes these satellites are collecting data at big pixels or little pixels. Sometimes they're collecting them really rapidly every day. Sometimes it takes a couple weeks for them to get back to the same spot. But in any case, collecting data remotely. They don't have to touch the planet to be able to get the data. So it's remotely sensed data. Now, this data, as I mentioned, is being broadcast across the electromagnetic spectrum. We can only see that tiny little itty bitty slice that we call visible light. Roy G. Biv, if you remember your acronyms, red, orange, yellow. I shouldn't have started this. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. It's actually backwards. Red are longer wavelengths and the violet are shorter wavelengths, but really don't vary much between the longest long wavelengths of like radio waves and the shortest of short wavelengths like gamma rays. You don't want to hang out with gamma rays. Avoid them. X-rays are fine in small doses. If you've gotten an X-ray, you've benefited from them. Radio waves, I don't think anyone listens to the radio anymore. So one of the challenges we have is that we have to represent all of this electromagnetic spectrum just using the tiny little slice of visible light that we can see. And the tiny little slice of visible light that we can see is limited by our eyes. There are other animals, insects and birds and other mammals and fish and every being on the planet that has the equivalent of eyes, ocular receptors, sees color differently. And we see color that is reflecting from a surface. So when you see red, red is reflecting from that object. When you see a green ball, green is reflecting from the object, so on and so on and so on. So we have to use our eyes, which are very limited in terms of what they can see. We have to use that spectrum of what our eyes can see to represent the whole rest of this electromagnetic spectrum. And in fact, we're really interested in remote sensing data in a lot of infrared data and a lot of ultraviolet data. And if you're into astronomy, you're into X-rays and gamma rays and stuff like that. Quick, look at these two squares. Do you see the little squares inside of them? Think to yourself, are the little squares different colors? They're the same color. Isn't that cool? And it's because our eyes are garbage sometimes and they get confused by the light and the dark around them. So these interior squares, 1 and 2, are the same color. Quick, what about those orange dots in the lower right-hand corner of this slide? Are those oranges different colors? No. Again, something in shadow, something in light. Our eyes struggle. We can see 10 million colors, but that's not quite enough to see all of the different data that we can see. We've talked about color vision deficiencies before. So some people can see less colors. Some people can actually see more colors. Their cones are hyperactive, and especially into the infrared. So imagine being able to see infrared. Ooh, be fun. See heat. Here's some infrared data. So we use color scales. We use colors that are warm or cool. We use colors that traditionally represent things to then clarify when we're looking at infrared data. So there's a house. You ever have an infrared camera on you? It's fun to look at houses, see where all the heat is leaving. The hotter parts of these houses are in white and red because those are hot colors. And the cooler parts of these houses are in blue because that's a cooler color. So we use these regularly as we're looking at remotely sensed data. We're trying to understand all of this information. So for us, a leaf is green. It's reflecting green light. But vegetation actually really reflects infrared light. So often when we're looking at vegetation data, it shows up as very red because we use red to represent infrared radiation. We call this idea, or we call this structure, reflectance spectra. Every thing that we have sensed, we have tried to understand how it reflects electromagnetic information, because the visible slice is very narrow, but the infrared slices are much bigger. So we can see more. We can understand more about vegetation or soil or minerals. All these different pieces, if we start to understand better how they reflect different types of electromagnetic information. Look at that little bump. If you look at the little bump here at healthy vegetation, has that little bump in green. Green, good. We can see green, but a much bigger bump at the near infrared. So remotely sensed data allows us to see things from orbit, to understand the planet without having to go to a place to collect data. It allows us to see different spectrums. It allows us to see electromagnetic data we can't see with just our eyes. It allows us to build up a better understanding of what the planet is and what the planet looks like, and how the planet is changing. And as we saw in the first video, I think it was, we can stack these layers together to make photorealistic data. You stack red, green, and blue, you got a photo. You stack blue, green, and infrared, you get something else. There's all these combinations you can do. Stack all the infrareds and figure out what's wrong with your vegetation. So seeing is our last task of our topic on rasters and remote sensing here. This is a little site called Earth Engine from Google. It's linked on our Moodle page. Earth Engine is a collection of historical Landsat imagery. Landsat is a remote sensing platform. Landsats have been up for a long time, collecting data about the Earth. Google has ingested all of the Landsat data because Google's got big servers and good internet. And they've put all the Landsats into Earth Engine. This time-lapse viewer allows you to be able to work with and look at the changes of that data over time. So click on that link. There's a bunch of preset options when you click on this link. Glaciers melting, water disappearing in the American West, the RLC, real exciting stuff. Or you can find your own place. And as you do that, think about what you can see. Because remote sensing, most of all, is about what you can see.